Uh, hey. So we're going to start talking about viscosity. Viscosity is a fluid property that you don't have as much familiarity with. It's the degree to which essentially fluid resists flowing. So things with high viscosity resist flow more. Things with low viscosity resist flow less. Air, if you move your hand through air, it really doesn't resist flow much at all. If you move your hand through water, of course, that's much harder. So we expect water, has a higher viscosity than air. So let's take a look at exactly how viscosity works. We're going to consider two plates separated by a distance h. So we're going to have these two plates, and they're going to be separated by some distance, which we're going to call h. And we're going to imagine that the bottom plate is fixed and the top plate is moving. We have our x and y coordinates there. And so I say there's some h distance here in between the plates, and of course the interspatial gap is filled with a fluid. So this plate is moving, and it's going to take some amount of force to keep that plate going. And the question is going to be, how much force does that really take? And we're going to be able to calculate that, and we're going to see that how much force that takes really does depend on the viscosity of the fluid. So that's going to be the thing that tells us how hard it is to move that plate, because the only thing resisting the flow, the movement of that plate, is the fluid itself. We're going to define a velocity here. This will be consistent in the class. It'll be u. It'll be the x velocity. So u will be the x velocity of the fluid for now. And so that's what we need for that. So now we're going to prove later that the velocity profile of the fluid between the plates will be linear for steady motion. So if we move the top plate in a steady way, meaning at a constant speed, for steady motion of top plate, the velocity profile will be linear. So what that means is that the velocity at the bottom is going to be 0 because this plate isn't moving. And then at the top, the plate is going to have some velocity. Let's say it's this amount. I'll draw it here. And in between, it's just simply a linear relationship based on position. So the velocity is 0 at the bottom because the plate is not moving. And the plate at the top is moving, and the velocity there is going to be some velocity. We're going to call it u0. So we'll say the plate velocity is equal to u0. Plate velocity is equal to big U0. So that's going to be the velocity of the plate. It's moving at a steady location. When we have a fluid that's in contact with a solid, we almost always have what's called the no-slip condition. So fluid in contact with solid follows the no-slip condition, almost always. So lacking other information, you should assume that if there's a fluid in contact with a solid, that the fluid is a no-slip. And what that means is that the fluid moves at the same velocity as the solid. Fluid and solid have same velocity at the interface of the two. So what that means for this problem is that at y equals 0, u equals 0, because we said that the bottom plate is not moving. And at y equals h, which is the top plate, the velocity of the fluid is going to be the same as the velocity of the plate, so that big U0. So that's what we're going to say is the no-slip condition, that the fluid velocities and the solid velocities match at the interface between the fluid and the solid. All right, so now we've got some information. We've got the velocity of the plate. We have the velocity of the fluid at different positions. And what that allows us to do is it allows us to actually calculate a derivative of the velocity. So du dy for this situation, and I can use a total derivative because u is only changing in the y direction. It's not changing in the x direction. The steady motion is the same all across the x domain, is equal to u0, which is the speed at the top of the flow, minus the speed at the bottom of the flow, which is 0, divided by the distance over which that occurs, which is h. And so we have a very simple relationship for the derivative, which is just u0 over h. And that's because it's a linear flow distribution inside that channel, going from u0, the top plate speed, to the bottom plate speed. For most fluids, this is true. F of x is equal to mu du dn times a. So this is the force exerted by the fluid on a plate, or on any surface really. So where the n is the direction perpendicular to the surface of the plate pointing into the fluid. N is direction perpendicular, I should say, to surface, pointing into the fluid. All right, so we're going to have this derivative. The direction of the derivative depends on which direction is pointing into the fluid. That little n hat there is pointing into the direction. In this particular case, n hat, therefore, is in the negative y direction, because from our top surface, the force exerted on the top plate is going to be the pointing straight down. So from the top plate, of course, pointing perpendicularly into the fluid, that would be our n hat. And of course, we can see that that is equal to the direction of negative y. So we're going to have a negative y there. So the force exerted by the fluid on the plate is going to be Fx equals mu minus du dy times the area of the plate. Mu is a property of the fluid, and that's what viscosity is. So mu is called the dynamic viscosity. We're going to see there are two types of viscosity. We're going to use them both, but mu is the symbol for the dynamic viscosity, and it's the one that goes into this relationship for force. So force exerted on top of the plate by the fluid, as we said, in this case, we have mu, we have du dy, but we know du dy from here, so we can plug that in, right? So we're going to plug that in there, and we're going to say that the force exerted on the plate by the fluid is negative mu u naught over h times the area of the plate. So that's it. If we wanted to actually solve this, of course, we would need the area of the plate, and we would need some actual velocity. But as some examples of the mu's, which I say depend on the fluid, mu for water is approximately 0.01 grams per centimeter second, which is equal to 0.001, stupid, 001, not 0001, sorry, 0.001 kilograms per meter second, and that's at 20 degrees C. Mu for air is equal to 1.81 times 10 to the minus fifth kilograms per meter second, also at T equals 20 degrees C and P equals 1 atmosphere. So quite a big difference there. We've got a much, much larger viscosity for water than for air, almost a factor of 100. And if you looked at molasses, obviously a highly viscous substance, that's 50 to 100 kilograms per meter second. So we see that the viscosity can change by a large amount, literally a factor of like 10,000 or more, as we go from air to water to molasses. So Viscosity really does change a lot depending on the fluid. It is also highly dependent on temperature, and we'll see that in the next lecture.